Over a century ago, physicists were trying to figure out what made hot objects glow, which ultimately led to the ultraviolet catastrophe, a discovery that unveiled one of the largest flaws in physics. At the turn of the 20th century, Max Planck introduced his quantized light postulate, which was a derivative of his law of blackbody radiation. To understand how radiation is emitted for all objects and how the wavelength of radiation varies with temperature, experiments involving the behavior of standard objects called blackbodies were required. A blackbody is an object that is a perfect absorber of all wavelengths of radiation incident on it. When a blackbody is heated to a certain temperature, it starts to emit radiation depending on the temperature the body is heated to. The radiation emitted from a blackbody extends over all wavelengths of the electromagnetic spectrum. However, the relative intensity at each wavelength varies considerably and is characteristic of a specific temperature. Anyone who's used a toaster before will have noticed that when the heating elements get hot, they start to emit light. Initially, when they're warming up, the colour is dark red. When they get hotter, they get brighter, and the colour is more orange. Classical physics suggested that an ideal blackbody will emit radiation in all frequency ranges, emitting more energy as frequency increases. This was seen as the classical wave theory. This classical wave theory predicted that the intensity should increase as the wavelength decreased. The experimental data matched this classical theory for the regions of lower wavelength. However, the theory proposed that as the wavelength becomes shorter, the radiation intensity would increase exponentially, which was not found to be the case in the conducted experiments. The notion that the intensity of the radiation emitted from the blackbody would approach affinity as wavelength decreased was known as the ultraviolet catastrophe. It is such a catastrophe as it violates the principle of conservation of energy and simply could not be explained by existing theories. The experimental data from blackbody experiments revealed that the radiation intensity curve corresponding to a different temperature has a definite peak, passing through a maximum and then declining. This is what could not be explained. A German scientist by the name of Max Planck came up with a revolutionary idea to explain the problem with the results observed in the experiments. Planck introduced a postulate stating that the radiation or energy emitted from a blackbody is not continuous, but it is emitted as packets of energy called quanta or photons. Planck thought, what if each oscillator in a blackbody can have an energy which is an integer multiple of a minuscule value h? This assumption allowed Planck to derive a formula for the entire spectrum of the radiation emitted by a blackbody. E equals hf, where E is energy carried by a photon, h is Planck's constant, and f is the frequency of the wave. There were many positive implications of classical scientists uncovering the ultraviolet catastrophe and Planck's postulate explaining the distribution of blackbody radiation. It literally took an Einstein to combine this postulate and the particle light model to then explain the photoelectric effect, also opening the door to the entire field of quantum mechanics.